Good morning, students. Today we will discuss about compound bars. Compound bars. Compound bars means what? If two or more bars are together resisting the force applied to that. For example, this is a one bar made up of one material and another bar is again made up of another material. Maybe both might be fixed with some support, between some support, and after that it might be undergone with some stresses. Which type of stress? No need to worry about that in the compound bar definition. Therefore it is undergoing some stress. Sometimes it might happen like this also, that one bar is here and another bar is connected to that, both are fixed between the supports, and now it might be undergone with some force here. Then also it is a compound bar. Not only in horizontal cases in all the way, even though in a vertical case as well. For example, this is a cylinder. It looks like a cylinder in a top view, and inside one space, and there another material is kept. The surround, this is another material is kept, and maybe it is fixed between the two supports or otherwise the top support, and it is pulled in downward direction. Then this force is resisted by this member and this member. Again, this is the compound stress analysis. Sometimes in a horizontal bar, rigid bar will be there, and this rigid bar is hanging between the two supports, hanging between two strings, and the force is applied here. When this force is applied, this string and this string starts resisting that. Okay, this also comes under compound bar analysis. Not only purely hanging, sometimes if it is fixed between this is hinged at one point and connected to one side and another side. Again it is pulled by some force. This rigid bar is this string, and this string will be resisting this force. Therefore again this comes under compound bar analysis. Means the definition of compound bar is two or more than two bars collectively resisting the forces. Okay, that is compound bar. Okay, we will solve few problems on this, and before solving the problems I would like to explain you how, in what way we are analyzing this. See, analysis. See, one thing you should be very clear, that if the bar is there here, if I pull this bar in one direction, there is no resistance in this direction. If I pull this one, it will travel in this direction. When it moves in this direction, I will not observe any resistance offered by the body. There won't be any resistance, this force, because I am pulling and it is following. Okay. When it is following it completely, when I am pulling this one and it is following, then I will not observe any change in length. I will not observe any change in length here. That I will not observe any change in length in the bar. Means we will not observe any deformation. Then when we will observe deformation is, if I apply P in this direction, then there should be a resistance equal to the applied force. When this force and this force is same, then this body is in equilibrium. This body is in equilibrium. When the body is in equilibrium, then only the deformation can be observed. Okay, means to observe any deformation or to build the resistance. The first one, to observe any deformation or to build the resistance. What is necessary? The necessary is equilibrium condition. Equilibrium condition is necessary. Therefore, whenever the problem is given, first thing you need to check whether the body is in equilibrium or not. How to check that? That is sigma summation of fx equal to 0. All the forces in x direction must be equal to 0. all the forces in y direction must be equal to 0, all the moments at any point equal to 0. Then if these three conditions depending on the orientation of the bar, if the bar is oriented horizontally and the forces are only in horizontal direction, this condition is enough. If the bar is horizontally and the forces are in the other direction, then this and this is enough. No horizontal forces here. If the bar is subjected to all horizontal forces, concurrent forces, non-concurrent forces, then all three conditions are important. Therefore, again, depending on the orientation of the structure, we need to check its equilibrium condition. If the condition is equilibrium, if the body is in equilibrium, then I will go to compatibility condition. The second conditions are called as compatibility condition. Compatibility condition. I say, instead of calling compatibility condition, I personally call this one as a common sense. Common sense. What is that common sense? See here, when I pull this bar this side, then this section will move here. When this section moves here, and the same thing means this bar is contracted, means this bar is resisting. When I pull this one this direction, then it will come down. When it come down, this bar and this bar both comes down with equal proportion, equal length, distance. When I pull this force downward, keeping this one as a horizontal, then the deformation in this bar and this bar is same. These are somewhat common senses. Means deformation conditions, compatibility in deformation. Compatibility in deformation conditions I need to apply. If I am able to apply equilibrium condition, if I am able to apply compatibility condition, then the problem is completely solved. All the unknowns present inside the body can be determined. Okay. Therefore, whatever the problem from the next slide onwards I explain, all the problems, first you need to consider equilibrium condition, and the second you need to consider compatibility or deformation conditions. If those are satisfied, then the rest all is just a pure mathematics. With the help of mathematics, we will analyze all the forces, stresses or deformations present in the bar. Okay, we'll go one by one, we'll understand how to solve that. Okay. Now look at this problem. The compound bar of a length 500 mm consists of strip aluminium 50 mm by 20 mm. See here, the dimensions are given 50 mm by 20 mm thick, and a strip of a steel 50 mm wide and 15 mm thick, rigidly joined at ends. If the bar is subjected to load of 50 kN, find the stress developed in the bar in each material and the extension of the bar. Take elastic modulus of aluminium and steel is 1 into 10 raised to 5 Newton per mm square, 2 into 10 raised to 5 Newton per mm square respectively. See, the figure is given here. This we will call it as a steel bar, this is a steel bar, and this we will call it as a aluminium bar. Then cross sectional, if I see, it look like this. This is your aluminium bar, steel bar, and we have another here. This is steel bar. Okay, and this width is 50 mm, and this width is also 50 mm. But aluminium is of 50 and 20 mm. This is a 20 mm, and this is 15 mm. These data are given here. Using these data, we need to go ahead. And here, one load is given, that is 50 kilonewton. Okay. The first condition is, I need to draw the free body diagram. This is one bar, and this is another bar connected here, and both are pulled by the force. 50 kilonewton. Then to make it equilibrium, there will be some force here and here developed. Let us consider this force developed. I will call it as a PA, and this force I will call it as a PS. PA, P aluminium, P steel. Then I need to first satisfy the equilibrium condition, that is summation of Fx equal to 0. Fx equal to 0, if I see here, there are no horizontal forces, therefore no use of this equation. Go to the second equation, summation of Fy equal to 0. Here I will see forces are there. Upward force I will consider positive, upward force Pa positive and downward force negative, that equal to 0. Then Ps plus Pa equal to 50 kilonewton. I got one equation. And after that I need to go to the compatibility condition. The compatibility condition says that this section, when it is pulled in downward direction, it will yield delta L. Then delta L for aluminium, delta L for steel, both will be same, because this bar will pull it in the same direction, same deformation. Therefore delta L for aluminium will be equal to delta L for steel. And we know the equation for prismatic bar, PALA by AAEA, that equal to PSLS by ASES. Now in this problem, that length is same, because see here, the length is from here to here, it is the same length. Therefore the lengths will be cancelled. Then you got PA as unknown, and AA is the area of aluminium this side, that is 50 into 20. 50 into 20 is the aluminium. Then EA is aluminium Young's modulus is 1 into 10 raised to 5. 1 into 10 raised to 5. That equal to PS unknown divided by, this is 50 into 15 into 2 into 10 raised to 5. 10 raised to 5, 10 raised to 5 cancel, 50, 50 cancel, and then this is the 30 and this is the 20. Therefore I got here, that is PA by 20 equal to PS by 30. Therefore PA equal to 2 by 3 PS, or PA equal to 2 by 3 means what? 0.67 PS. This equation I got. Now see here, I got one equation, the relation between PA and PS, and I got another equation, the relation between PA and PS. Therefore I will substitute the second in the one. Then what happens? The first equation is PA plus PS equal to 50 kilonewton, and the second equation is PA equal to 0.67 PS. This is 0.67 PS plus PS equal to 50. Then PS is taken common, 1.67 equal to 50. Then PS equal to 50 divided by 1.67, that equal to 50 divided by 1.67 is 29.94. 29.94 kilonewton is your PS. When PS is this much, by using the first equation I will get a PA also. PA equal to 50 minus 29.9, that is 20.05. 20.05 kilonewton. Means here I got PA. Okay, the forces in the members I got. Stresses in the members, if you want, that is sigma S equal to PS divided by AS, and sigma A equal to PA divided by AA. Sigma S is PS. PS is 29.9 into 10 raised to 3 Newton divided by area of the steel is 50 into 15. Therefore the answer is 29.9 into 10 raised to 3 divided by 50 into 15 is 39.86 MPa. 39.86 megapascal or Newton per mm square. I got stress in steel. The same way, stress in aluminum is Pa. Pa is 20 into 10 raised to 3 Newton. This is mm square. Divided by area of the aluminum is 50 into 30. 30 or 20? Check it. 50 into 20. 50 into 20, that equal to 20 into 10 raised to 3 divided by 50 into 20. That is 20 Newton per mm square or 20 MPa. Okay, we got a stress. Then what will be the axial deformation of this bar? Then you can take delta L aluminum or delta LS. I will take delta LA, that is PA LA divided by AA EA. Then PA is 20 into 10 raised to 3 LA given. How much given? Length is 500 mm. The length is 500 mm divided by area aluminum is 50 into 20 into 1 into 10 raised to 5. That's 20 into 3 into 50 divided by 20 into 10 raised to 3 into 500 divided by 50 into 20 into 1 into 10 raised to 5. The answer is 0.1 mm. 0.1 mm. Oh, the problem is solved. The next problem will go. This is the next problem. You can do it as a homework because this and the previous problem which is solved, both are same, but only little difference in the orientation or otherwise in the diagram. Okay, now see, a compound bar consists of a circular rod, steel, diameter 20 mm, rigidly fitted into the copper bar tube in internal diameter 20 mm. And thickness is fitted into a copper tube internal diameter 20 mm and the thickness is 5 mm as shown in the figure. If the bar is subjected to load of 100 kilonewton, find the stresses developed in the bar in the two material. Simple. They did not told whether it is vertically hanging or horizontal. Therefore, nothing to worry. We will consider vertical only. This is one, and this is another, like this. Okay, and it is pulled means for equilibrium, PC plus PS equal to 100 kilonewton, and for displacement delta C equal to delta S. And use these two equations, you will get the answer. I will give the answer. You have only thing you need to worry is what is area of aluminum, copper, and area of steel. You should be very clear about these two parameters. Then take the answer as PC will come. PC is getting 42.857 kilonewton and P steel is 57.143. 57.143 is the PC. PS. Okay na? Then after this PC by area, PS by area we will do, and you will get a stress in the steel is 181.89 MPa, and stress in the copper you will get 109.12 Welcome back. In last class we discussed about compound bar problems, and a few more problems I am going to solve now. See here, the problem is the reinforced concrete column of size 230 mm and 400 mm has 8 bars of 12 mm diameter as shown in the figure. Here the figure is there. Here this is the cross section of the column, and 400 mm is the width and 230 mm is the breadth. And here how many bars are there? 3 plus 3 plus 3. 8 bars are there. 8 are what? 3 plus 3, 9 bars are there. But here they said that 8 steel bars of 12 mm diameter as shown in the figure. If the column is subjected to axial compression of 600 kilonewton, find the stress developed in the steel concrete. Okay, I think here 8 bar is mentioned, so this bar we will ignore it. Okay, there is no bar such here, only 8. 1 2 3 4 5 6 7 8. 8 bars are there of diameter 12 mm, right? And they are of steel. And something here it is given, that is the take modular ratio as ES by EC equal to 18.67. Okay, this is a ratio, therefore there is no unit. And here they have not given you directly the value of ES and the value of EC. These two, the ratio of these two is given. Don't worry, wherever we require it, we will use it. First, what I said in the previous lecture is that you need to satisfy the equilibrium condition. See, the column means it will be in the vertical position and it will be having some supports at top and bottom. Okay, and the force it is acting at the top is how much? 600 kilonewton. 600 kilonewton force is acting at the top and it is resisting. But who is resisting the force? Concrete and steel, both are resisting the 600 kilonewton. Therefore, for equilibrium conditions, I will write that is the force applied, that is the 600 kilonewton will be resisted by that is a PS steel plus PC concrete. Okay, this equation I got it for as an equilibrium equation. And the second one is the compatibility condition. When this is pushed here and this will enter inside with the same distance, that is the delta L. That delta LS equal to delta LC. Then delta L is equal to PS LS divided by AS ES equal to and PC LC by AC EC. And here the length will be same from the top to bottom. The length is same for the both, therefore length is cancelled. Then I want what is AS and AC, that is the area of concrete and area of steel I want. First I will calculate steel. Each of circular bar, therefore 12 mm in diameter, therefore pi by 4 into 12 square is a 1 bar area, such 8 bars are there. Therefore this is pi by 4 into 12 square, 0.785 into 12 into 12 into 8. The area is 904.32 mm square. And the total this rectangular box area is, that box area is 400 by 230, that is 400 into 230, that is 9200 mm square. Okay, and what is the area of the concrete is? Area of the concrete equal to that box area minus that is your area of steel. Therefore 9200 minus 904.32, that is 91, the answer is 91095.68 mm square. This is area of the concrete, right? Now we got areas, and I can substitute here, I can bring those two and substitute in this equation, that is PS divided by PS divided by AS is 904.32, and ES I don't know, I will write it ES as it is, and that equal to PC divided by, this is a 91095.68 into EC. Okay, now what I do, I will put PS here and everything I will send that side. That becomes 904.32 EC, ES, and PC I will write here, divided by then 91095.68 EC. Now if you see here, in the problem it is given EC by ES by EC equal to 18.67. Directly I can write in this place, that is 18.67. Then I will calculate in the calculator, that is 904.32 into 18.67 divided by 91095.68. Then I will get answer 0.185. Okay, I am getting here PS equal to 0.185 PC. Very important. Okay, then if I calculate, then by using a PS plus PC equal to 600 kilonewton, and another equation now I got as PS equal to 0.185 PC, correct? 0.185 PC. Then I will substitute this PS in this place, that is 0.185 PC plus PC equal to 600 kilonewton. Then PC taken common, then it becomes 1.185 PC equal to 600. Then PC equal to 600 divided by 1.185. Then the answer is 506.18 kilonewton. This is a PC. Then PS will be equal to 0.185 PC, therefore into 0.185, that is 93.64. 93.64 kilonewton. Then go ahead, you already know how to calculate stress in the concrete, that is a PC by AC, and stress in a steel, that is a PS by AS, and the deformation delta LC equal to PC LC by AC EC. If everything is known, you can calculate this. Okay, the problem is solved. Going to the next problem. Here this is a somewhat tricky problem that I am going to solve now. 3 pillars, 2 of aluminium and 1 of steel. 2 of aluminium means what? This is aluminium and this is aluminium, and steel is in between. Steel support a rigid platform 20 kilonewton as shown in the figure. Area of each aluminium pillar is 100 mm square, and that of the steel is 800 mm square, 1000 mm square and 800 mm square. Aluminium is 1000 mm square and steel is 800 mm square. Find the stresses developed in the each pillar. Then take a this, what is that? Take EA, Young's modulus for aluminium is this much, Young's modulus for steel is this much. What additional load P can it take? Working stress are 65 Newton per mm square and aluminium and aluminium and 150 Newton per mm square in steel. Okay, leave out this one. This is solution part. It's by mistake it came. Now what you need to do? Again the same thing. First draw the free body diagram. The free body diagram if I draw, Let us consider this 1000 Newton is acting. This is acting like this. Okay, means this force is divided for this, and this aluminum bar is here which resists that one. This steel bar here that resists that one. This aluminum bar that resists that one. Therefore, this we will call it as a PA, and this is also PA. This is a PS. Therefore, the equilibrium condition, if I write, this is your 200 kilonewton. 200 kilonewton weight it is given here. Now, if for the first condition, what is that? For the first condition, this equilibrium condition is downward 200 plus upward PA plus upward PS plus upward PA equal to 0. Therefore, 2PA plus PS equal to 200. This I got. Right? Then equilibrium condition, this deformation condition, if I apply, delta LS equal to delta LA, then delta LS equal to PS LS by AS ES equal to PA AA PA LA by AA EA. Okay, now L is not constant, we cannot cancel this one. Then after this, you write it here, PS I don't know, LS is how much? Steel length is 250 divided by area of steel is 800 and Young's modulus of steel 2 into 10 raised to 5, that equal to PA. Area length of this one is 200 divided by area is 1000 into 1 into 10 raised to 5. Therefore, if I work this one, then I will get a 250 divided by 800 into 2 into 10 raised to 5. This side I got. First what I will do, we will cancel few of the things. This what 10 to the power cancel. This 1 0 cancel, and here 2 zeros and here 2 zeros cancel. Okay, now next is here 25 divided by 8 into 2. Therefore, here I got 1.562 PS equal to that side what I got 20 divided by 10 into 1, that is 2. This side I got 2 PA. Therefore, PS equal to 2 divided by 1.562 1.28 PA. This much I got. Okay. Now coming to the equation, that is a 2 PA plus PS equal to how much? 200 kilonewton. That equal to 200 kilonewton. Then PA is how much? Sorry, PS is 1.28 PA. Therefore, here let it be 2 PA, 1.28 PA plus it is 1.28 PA equal to 200. Therefore, 3.28 PA equal to 200. Therefore, PA equal to 3.28, 200 divided by 3.28. This is 60.97 kilonewton, and PS is how much? You can calculate PS as 1.28 PA. Therefore, into 1.28, PS is 70.04. I got P. Then if you want the stresses, then stresses in aluminum equal to force in the aluminum is 60.97, area of the aluminum is 1000 mm square. Okay, this is kilonewton per mm square. like that, write the answer. Then stress in the steel equal to force in the steel 70.04. okay, here not kilo, 10 raised to 3 will write 70.4 into 10 raised to 3 divided by 800 mm square means kilonewton, sorry, Newton per mm square. Then solve this one. Okay, the problem is solved. The second, here one more additional thing is given here, that is additional load carrying capacity. That is additional load carrying capacity. Additional load carrying capacity, that how we need to calculate. The first one, there are two things it is given. The first one is, here in the problem it is given that working stress is 65 Newton per mm square in aluminium. Okay na? Therefore, if PA governs the load carrying capacity, PA governs the load carrying capacity means what? If everything is resisted by PA, means PA is a leader. Okay, if that is the case, then I will write a PA equal to 65 kilonewton per mm square, sorry, Newton per mm square. Then PA equal to, I will get a PA equal to this much Newton per mm, sorry, Newton only. This is a small PA or sigma A given, no? Sigma A is given, it is not calculated sigma A. Here also you calculated sigma A, sigma S, but I am not taking that. In the problem it is given, that's why this is the second part of the problem. Sigma A, if I take 65 Newton per mm square, then sigma S I will get the first. Then if I get this one, then PA will be equal to 65 into area now. Area is 1000. Therefore, 65,000 Newton per mm square it is. Now, if I want PS, that is 1.28 PA. Therefore, 65,000 into 1.28 is 83,200. I will get 83,200 kilonewton. Sorry, Newton. PS I will get. Then PA and PS I got. PA and PS I got. Then the total load carrying capacity becomes what? Total load carrying capacity becomes 2PA plus PS. That is a 2 into 65,000 plus PS is 83,200. Then this answer will be 213.2 kilonewton. Now it is kilonewton. This is the first condition, means if sigma A is governing. Then the second condition is if sigma S is governing. Sigma S is given in the problem as 150 Newton per mm square. Then I will get PS equal to 150 into 800, because 800 is the area. Then I will get 12,000, 1,20,000. What? 150 into 800, 1,20,000. 1,20,000 I got. This is the PS. Then PA equal to PS divided by 1.28. Therefore, PA equal to 93750 MPa. Then I got PA. Then the total load carrying by that one is 2PA plus PS. Substitute PA here and PS here. You will get 307.5 kilonewton. Hence, the actual load carrying capacity is 213. Means what? If you apply this much, steel is ready to take, but aluminum is ready to take only 213. Therefore, I need to carry only 213 weight. Only 213 weight. Okay, na? Therefore, the additional load carrying capacity is what? Now already 200 kilonewton is taking, but it can take 213. Therefore, additionally 13.2 kilonewton it can take. It can take additionally 13.2 kilonewton. Right? Thank you very much. The next problem here is a rigid bar AB 9 meters long is suspended by two vertical rods at its end A and B hangs in a horizontal position by its own weight. The rod at A is brass, the length 3 meter, cross sectional area 100 mm square, Young's modulus 1 in 10 raised to 5 Newton per mm square. The total rod, the rod at B is steel, length 5 meter, cross sectional area is 445 mm square, and ES equal to 2 into 10 raised to 5 Newton per mm square. At what distance D from A may a vertical load P equal to 3000 Newton be applied if the bar is to maintain horizontal even after the load is applied? See, this much of statement it is given, but the actually speaking figure is not given. This figure I have drawn it. This is not given in the question. By reading the question we need to draw the figure. Right? Just you go through each and every sentences and parts of the sentences, then you will get this picture. And after this, if you want a free body diagram, let us consider I will cut this one, then I will have a force in upward direction. Then I will cut this one, then I will have a force in upward direction. Let us consider this as a FB and this as a FA. Sorry, what is it? FS. Okay, no? FS. Then what is the equilibrium condition? Equilibrium condition is FA upwards and FB upwards, then FS upwards, the minus 3000 Newton downwards. Okay, na? Equal to 0. Therefore, FB plus FS equal to 3000 Newton. One equation. When this force is applied here, this bar will horizontally come down. This bar will horizontally come down. Therefore, the distance deformation in the brass is same as deformation in the steel. Therefore, delta LB equal to delta LS. Then FB LB by AB EB equal to FS LS by AS ES. Continue. Okay, now here substitute all the variables here, this one values here, and after that you will get FB equal to something into FS. You will get this. Then after that you substitute here, you will get FA, FB value and FS value. You will get both. Then after that stress you can calculate. Thank you very much. This way all compound bars problems you can solve, and refer some textbook and solve many problems. Okay, we'll end the lecture here. Thank you.